Thank you all for making it out this afternoon. I am still not doing super great, but I'm getting better, so I think I will be able to return to work soon. It's been a very bad week for me, so I am sorry that I'm not able to be there with you on campus today. I'm doing the best I can. If you've tried to get a hold of me over the last week or so, I know I've been a little spotty. Reach out to me again, please, if you've not heard back to me yet. I've tried to catch up on stuff that I've been missing, and I feel like I'm probably still missing some stuff. So if you, excuse me, if you need something from me and you haven't heard back, sorry about that. Yeah, please reach out again. And sorry about the last week or so. It's been rough, but I'm getting through it. Today we are talking about a very important topic, and I want to remind you all actually of a couple of things. First off, last week I mentioned it was very, very important that you understand the material from last week before attempting the material that we're about to talk about this week, and that is still very much true. That is still very much the case. So if you are still struggling with the Module 5 material, if you haven't even gotten around to the Module 5 material yet because of life or other stuff, I completely understand. That is totally okay, but you know, this may not be the best place for you to be right now, to be perfectly honest with you. You will not understand what I'm talking about today unless you have at least a basic grasp of methods that we talked about last week. It will not happen. So instead of trying to struggle through because you feel like you have to, I would actually encourage you to go back and review that material if you have to. Set up an appointment with me if you have to. I'd be happy to go through it with you in my office when I'm feeling better. Whatever you need to get you back on track. I know this stuff is hard, but banging your head up against this topic isn't necessarily the right way to solve it. Sometimes the right thing to do is to go back and study up, make sure you understand methods first, and then try to come back to this stuff. So what I'm going to do today is introduce, I believe, 3 recursive examples for you. You're welcome to ask questions in chat. So I've got all the mics off, so please use chat if you ever have any questions. I've got chat open. Welcome to holler at me anytime. And yeah, let's just hop right into it. The first example that I want to start off with is a very, very simple one. We're going to start off with factorial. And just as a little refresher, since I know factorial is not the most frequently used mathematical operation out there, recall that 5 factorial is saying 5 times 4 times 3 times 2 times 1. And so we wish to write a method to compute this for us. And I think it's actually important to note that we could do this with loops. In fact, I'm going to go ahead and code one up for us right now that uses loops. So stick a while loop in there. We probably need a result value. Actually, since we're doing multiplication here, 0 is not a good starting value, right? So we probably want to start out with 1. And then inside of the loop here, we can actually just do our multiplication. Results is equal to results times n. And then we have to decrease n by 1 each time. Or if that doesn't sit right with you, you could also make a loop variable. Maybe this is a little better, actually. Let's maybe, I don't know. Both ways are fine, right? I is less than n. Okay, I'm doing it both ways now. There we go. This way, I think, is maybe a little bit nicer because n stays constant. I'm not changing n, so I think maybe I like this way just a slight bit more, but honestly, I think the original way I wrote it out would have gotten us there. And then finally, we're going to return our result here. So if we look at what this does as we go through our loop, actually we don't want I to start at 0, do we? For the same reasons that I talked about before. 0 and multiplication do not mix well together. So we'll start I at 1. So the first time through, it's going to be 1 times 1. Second time through, it'll be 2 times 1. Third time through, it'll be 3 times 2. You can see, hopefully, that this will get us to our desired results. And if I come up here and call this real quick, for the value of 5, we should be able to see that successfully get computed and printed. So there's the value of 24. I can plug in a different value. These grow pretty quick, so don't plug in anything too big or it will get outrageously large. But this does appear to be properly computing the factorial for me using a very simple while loop. So does anybody, I know we haven't talked anything about recursion yet. That's my next step. But if anybody has any confusion about what this method is doing, I did go through it pretty quickly. Again, I'm sort of operating under the assumption that you understand that methods have a return value, and this one has a return type of int, right? If those are still a little rusty for you, please ask. I'm happy to go over those now. If you are still unsure about what I'm doing or why. But let's talk about how we could approach this a slightly different way using recursion. So a recursive method is any method that calls itself. And so what that means is that for any method to be recursive, all I have to do is take the name of the method and stick it down in here somewhere, right? So I do have to follow the proper method call syntax. So I do have to plug in a value for n, right? But officially, this method is now quote unquote recursive, even though it is not in any way, shape, or form accomplishing the goal that we've set out to do. But I do want to make it clear that at its bare level, at its bare definition, what is recursion? Recursion is simply a method that calls itself. So inside the body of the method, I expect to see a method call to that very same method. And this is, of course, a little bit mind-bending, right? But if you have been paying attention to how we've been talking about methods, I think it's important to understand that every time I call a method that is operating independently, right? So it's like I'm creating this brand new independent walkthrough that's going to take place. And so it is entirely reasonable, in fact, desirable in some situations to do this. So if we want to use recursion in a more effective way, there are a couple things we need to kind of pay attention to, kind of keep in mind as we use recursion. Not just going to slap it in anywhere that we feel like it. We're going to try and approach this in a logical way. Let's look at the loop up here and see that, okay, the loop is doing the multiplication, right? So inside of this loop, I see some multiplication. And every time I go through that loop, I see that this value of I is going up, or the way that I had it written out before, I had it as the value of n is going down. If we look at the definition of recursion here, you can see it actually does seem to lend itself to a going downwards type of trajectory. In fact, 5 factorial, goes 5, 4, 3, 2, 1, 6 factorial would go 6, 5, 4, 3, 2, 1, etc. So using that kind of idea in mind, we can have this idea that the last value is always going to be 1. The last value that I get to, the last value that I need to multiply by is going to be 1. And some of you might be thinking, well, I don't even need to do that one, right? Because what's multiplying by 1 do for us anyway? But for the sake of argument, we'll assume that this is always the last value. So what does that mean for us? That means that if we are computing a factorial, right, and I am ever asked to compute the factorial of 1, right, I know that I must be at the end. I must be at the end of my factorial computing journey because I've reached the final term, this 1 term. Or another way of saying this is that the factorial of 1, or 1 factorial, is a known value. 1 factorial is equal to 1. I don't have to compute it. I know what it is. It is 1, right? It is defined as 1. In recursion, this actually ends up taking what's known as our base case. So in recursion, I would expect to see right off the bat an if statement. Notice I used a while loop up here, and I'm using an if statement down here. An if statement saying something along the lines of, okay, if n is equal to 1, I know what this answer is. I know that the factorial of 1 is 1, so I am finished. And if it's not 1, right, we probably have some more work to do. But if n is not 1, we know that we will eventually get to 1 eventually, right? Like that's just the definition of factorial. That's what's important about a base case. A base case is both a known value, something that we we know for a fact is well defined, but also is going to be something that all other cases travel towards. It is a natural sort of termination point for our repetition, for our recursion. So if we think about then, all right, in every other situation besides 1, what needs to happen? Well, let's take a look at our recursive definition, our definition of factorial up here, and see if we can't identify any patterns in here. See if we can't identify any recursion that is taking place in this definition. Specifically, notice that if I wanted to, I could actually extract another factorial out of this 5 factorial. This is a factorial right here. This is 4 factorial. So if I wanted to, I could write 5 factorial as being equal to 5 multiplied by 4 factorial. And think about what that means for us in terms of what we're doing today. We're talking about recursion. We're talking about a function calling itself, or a function being defined in terms of itself. And this is what we've hit upon right here, right? We've hit upon this, this magical, we would call this the recursive substructure. That is what this is called, where I have defined an operation, recursion, in terms of itself. Not recursion, factorial, sorry. I have defined factorial in terms of itself. I have defined 5 factorial, and it includes factorial as part of its answer, right? And if you wanted to, you could try to generalize this even more. So, okay, let's not just talk about 5 factorial, but let's talk about n factorial, right? So then for n factorial, what am I going to do? I'm going to say it's equal to n times n minus 1 factorial. Might wrap that in parentheses just to make sure it's extra clear what we're taking the factorial of, right? But you can verify this yourself just by working through this example, right? 4 factorial is equal to 4 times 3 times 2 times 1. But there's n minus 1 factorial right there. 3 factorial is right there. So I could actually write that as 3 factorial, correct? 3 factorial is 3 times 2. And this will work for any value of n that you could possibly conceive of. But this general case is very, very, very useful for us. This is going to become our recursive step. So every well-written recursive method is going to have 2 parts. I've already spoken about the first one, the base case. This is our stopping point. This is our well-defined value. This is when we know we've hit the end, right? We're at the bottom. There's nothing left for us to do. This is our recursive step. Let me label these here. This is our recursive step. So for our recursive step, this is where the recursive call is going to take place. And since we've already kind of done the math up here, I can actually just write this out directly, right? Where instead of using the exclamation point, I'll just use the method call to represent the fact that I'm doing factorial instead. So what does that look like? I'll return n times factorial recursion of n minus 1. And this here is going to be our completed definition of factorial using recursion. So I have them both up here on the screen for a reason. They're both performing the same operation. They're both using repetition to do it, right? It's necessary. You cannot compute factorial without some sort of repetition. But the one up here at the top uses a while loop to accomplish that repetition, while this option down here uses factorial, uses recursion to accomplish the repetition. I think what's really, really, really important, though, is to dive into this recursive solution and use the debugger to step through the stack and see what's really happening when we run through this code. So that's what I'm gonna do next. I'm gonna come up here and switch this out. I'm gonna turn my loop version off and switch it out for the recursive version. Recursion, sorry. And let me turn that down to 5, actually. And I'll go ahead and set my breakpoint here on line 16. And let's go ahead and step into this code and see what's happening when we run through this. See how it actually computes this factorial that we are trying to get at. All right, so as I switch into debug mode, here we are on line number 16 inside of my main method. And I do want to step into this line so that I can see how the recursive method is going to work. Notice over here on the left, before I do that, the only method on my stack right now is the main method, which is, that's expected, right? That's always what's going to be on the stack when we first start our program. So let's go ahead and step into this recursive method. And we see, okay, there it is. There is a recursive method appearing on the stack. I can see the value of n is equal to 5, just as I would expect it to be. So if we begin to step through this code now, I see that n is clearly not equal to 1. So I'll go ahead and skip through that and do my recursive step. This is going to tell us to do 5 multiplied by the recursive factorial of 4. So if I step into this method call now, notice what happens. Okay, there are now 2 copies of this recursive factorial method on my stack. I am now seeing that n is equal to 4 where I'm at. But why 2? Well, this one here for n is equal to 5, this is the one that we originally started with, right? It cannot do this multiplication until it knows what this value is. It has to figure out what this value is first before it can perform this multiplication. So it's waiting. This version of the method here, where n is equal to 5, is waiting. It's waiting for the version for n is equal to 4 to finish up and tell it what its answer is. But n is equal to 4 has to go figure that out. So let's step through this for n is equal to 4 and see what happens. We see that, okay, n is still not equal to 1, right? Still not equal to 1 here. So I'm going to skip my base case, jump down to my recursive step again, just like last time. And if I step into, hopefully not a surprise this time, I've got yet another one, right? So now I've got 2 versions of this method sitting here waiting. They're just waiting for the other method calls to finish up. They can't perform their work. They can't finish that multiplication until they hear what the answer is from that method call. So here we are. We're now in a third version of this method for n is equal to 3. I'm going to step through, still not at the base case, right? All right, I step down one more time. There's my 4th copy for n is equal to 2. Let's do this one more time. Step down to my recursive, step into, okay. Here I am now, whereas n is equal to 1. And if I look over here at my method stack, right, none of the methods that I have called so far have finished. Not a single one. They are all sitting there waiting, patiently waiting to hear back from all of the other methods that are above them in the stack before they can finish. And we're about to see what happens when we hit our base case, because we have finally hit the situation where n is equal to 1, and we know what that answer is. The answer is 1. So now I'm simply going to tell you, all right, the factorial of 1 is 1. That is what it is, and I will return that value. But where are we returning that value to? Well, remember the stack always tells us where we're going. So I'm going to take the answer of this method call, and I'm going to pass it up the stack to the method call that I was in just prior to this one. So this 1 is getting fed out of this method, and if I click the arrow this time, you'll see that, okay, my stack has shrunk. One of those 5 method calls has now finished. the base case knew what the answer was. It said, here's your answer, return a 1. It tells me it very much did return a 1. So now I'm back in the home where n is equal to 2. That's where I was just prior to this, right? So n is equal to 2. I now know that the answer to the last one was 1. So I can perform that multiplication now, right? 2 times 1 gets me 2. So the answer to 2 factorial must be 2. So if I step through this, you'll see that, okay, my stack is still steadily shrinking. That case where n is equal to 2, it was able to resolve itself. It knows its answer. It is 2. So it's going to take that 2. It's going to pass it up the stack. So now I can resolve the case where n is equal to 3. 3 is going to be multiplied by that last result that we got to get me the 6. That'll get passed up the stack, which now shrinks one more. 6 is going to get multiplied by the n value where I currently am at, which is 4, get passed up the stack. And now here I am. This is the original method call, right? This is the original place where I started. This is what I wanted to find out. This is n equals 5. This is my final result. So I see the result from 4 factorial got me 24. I can now plug that in here and get my final result, which should give me my answer of 120, which will then get printed out. So that recursive execution that I just walked you through is actually the same style of execution that I would expect to see for any recursive method. Obviously, recursive methods are going to do different kinds of tasks, different types of operations, but they are all going to work towards a base case, call more and more methods until they hit that base case. And then once that base case has been hit, they can start resolving all of those open method calls and working their way back up the method stack until they hit the original point of entry, and they have the final answer. So I know this is a difficult concept. This is actually probably the most important thing that I can talk to you about today. If anybody has any questions, I would love to hear them in chat. Happy to go through the debugger with this one again. If anybody would like to see that, please let me know what you're confused about. Please let me know what would help you. But if I don't see any questions, then the next thing that I would like to speak to you about is called the substitution method. So one of the things that I very much like to ask students to do to demonstrate their knowledge of recursion on an exam, for example, would be to show me the recursive execution of a method using something called the substitution method. And if you've been paying attention to the little exercise, that I just walked you through, we kind of already did the substitution method, but it's typically something that's often done on paper and pencil. You are going to be asked to do it for for the upcoming assignments and on the upcoming exam, which we'll be talking about soon. So I would like to walk through actually the substitution method now for this little factorial example, and show you exactly what that would look like should you be asked to do something similar on an exam or a homework assignment. So what we're asking is to compute the factorial. Well, I need to make comments here. So this is not code. This is normally I would actually prefer doing this on paper and pencil, but yeah. So we're asked to compute the factorial of 5, and as I said, we've determined the recursive substructure, which is that 5 factorial is going to be equal to 5 times the factorial of 4. And so what the substitution method says is, okay, well, I need to go figure out what this is now. I need to go figure out what the factorial of 4 is. So let me go ahead and put a new line here for factorial of 4. And I know that the factorial of 4 is going to be equal to 4 times the factorial of 3. And so now I have this new entry. What is the factorial of 3? Well, I have to go figure that out. Factorial of 3 is going to be equal to 3 multiplied by the factorial of 2. The factorial of 2 is going to be equal to 2 times the factorial of 1. And then finally, we've hit our base case again. The factorial of 1 is equal to 1. So if you're asked to write the substitution method, show substitution method for factorial of 5. This is the first part. We're actually not done yet, though. The reason that it's called the substitution method is because now that I know what this is, now that I know that the factorial of 1 is equal to 1, I can take this value and I can substitute it in. I can substitute it in up here. So now I can rewrite this entire line with the known value of factorial 1 substituted in. So that makes factorial of 2 equal to 2 times 1, which is equal to 2. And now, because I know what the factorial of 2 is, I can substitute that value in here and repeat that same process all the way back up. The factorial of 3 is now going to be equal to 3 times 2, which is 6. The factorial of 4 is equal to 4 times the factorial of 3, which was 6, which gives me 24. And then finally, the factorial of 5 is going to be equal to 5 times 24, which is 120. So the substitution method is really sort of just the paper and pencil way of writing out what the execution stack is going to be doing, what the computer is going to be doing as it recursively evaluates this method. So we go all the way down to the base case, and then once we hit the base case, we start substituting those values back in until we reach our original method call and get our final answer back out. Again, we walked through this in the debugger. We saw how it did all of this, but we could have predicted all of that exactly, right, on paper before we even did that. I think that's why the substitution method is such a powerful tool for understanding how recursive methods can operate. A big reason why I like to ask students to work through examples like this. Any questions about the substitution method before we switch to a different coding example? Excuse me. Okay. So the next example that I would like to talk to you about has to do with arrays. Hopefully arrays are getting to be a little bit more easy for you to work with. I wrote up this little array example before class that allows us to count how many odd values appear within an array. So I have created this little test array. You can see that the solution that I have given us uses a loop. So obviously I would like to work on the recursive version of this, but I do think it is very useful to kind of compare and contrast loops with recursion because they are both used for that same purpose, which is repetition. Both loops and recursion are two different tools for accomplishing repetition. So here's the loop version of what this might look like, and I'm not going to spend a whole lot of time on it. I feel like we've covered all this stuff. I hope that you feel comfortable enough with arrays and loops that you kind of understand what's going on, or you more than kind of understand. You do understand what's going on here. If you have any questions, please let me know. I'd be happy to explain this in more detail. What I would like to point out to you, though, is that when I try, let's say that I want to do this recursively. So I'll go ahead and start my my recursive version of this down here. So right off the bat, I sort of have a little bit of a hard time thinking about how to start my recursion, remembering that, okay, I've labeled this as a recursive method. That means that this method is going to repeat, right? And so I see that the first thing that looks like I need to do is make a variable for my counter and set that equal to 0. But how can I do that if I'm going to be repeating this method? Isn't this just going to erase my count and set to 0 every time this recursive method gets called? Like, how can I have this method repeat over and over and over again, but also still protect this so that it doesn't actually, get reset to 0 every single time? How can I actually, take care of that? Same thing with the, well, yeah, like making, that's actually not a good example. I think what's important to realize, though, is the fact that this does not get repeated. This piece of code here does not get repeated. It's not inside of the loop. It's only actually executing once. So including this piece of code inside of a recursive method that we are expecting to get repeated is not a reasonable expectation, right? Question in chat: is the substitution method like writing out each output for iterations? So iteration is not the same thing as recursion. The substitution method is writing out the output for the recursive method. I mean, I literally followed the recursive definition here, right? Factorial of 5 is equal to 5 times factorial of 4. I did not guess at this, right? I looked at the code and I copied it exactly from the recursive method. Great question, though. Please let me know if you have any other questions. So yeah, a lot of times we will have tasks that we wish to perform recursively, but they will have some non-repetitive components as part of them, right? And so in this case, the most common tool that we would use to help us would be something that is called a helper method. So a helper method allows us to separate the repetitive recursive stuff away from the non-repetitive non-recursive stuff. And so one thing to keep in mind as programmers is that you have a lot of power now. You have a lot of control now. If you wish to add another method to your code, I want you to feel empowered to do that. It is true there are some times that we give you code and we say, don't touch this. But I will very rarely be upset if you add additional things, right? Like that actually, to me, shows a lot of initiative, a lot of understanding of what is being asked of you. So if you wish to solve, solve a problem using 2 methods instead of just 1, right? Like I think that's not necessarily a bad idea. In fact, that's exactly what we're going to do here. I'm going to create a second method. I see a question in chat. Is there a reason you'd use recursion over a loop? That is an absolutely fantastic question. One that I am going to talk about in just a moment after I get through with this exercise. So yes, I will come back to that in just a second. I'm going to call this my helper method. Okay. So what does this let us do? This lets me put all of the non-repetitive stuff inside of the non-helper method, right? So all the stuff that happens once, it's going to go inside of the original non-recursive non-helper method. The helper method is the one that's going to be doing my recursion. It's the one that's going to be doing my repetition. It's the one that's going to need to have a base case and a recursive step. So in this particular case, let's talk about it. What is, how do we accomplish this? It looks like we're starting at an index of 0 and then just counting. So, we're just going to look at the number of odd values. And if the value at this first position is odd, then I've seen one odd value, right? Plus however many odd values there are in the rest of the array. So we just have to keep on counting. Every time through the recursive method, I'm going to look at one value from the array and ask, is it odd or not? And then, proceed on with the recursion. We need a way to keep track of where I am in this array, right? So something that is included for us in this loop, but that we don't have down here just yet, is our loop variable I. This is something else that only needs to get created once, right? So I'll do that up here. But then wait a second, how can I get this information down here? So we now have sort of a communication issue where I've created these up here in my non-helper part, but I somehow need to get this information down here, and then vice versa. Once this is done doing its work, I need to get its answer back to where I originally started. Well, we're going to call our helper method. And we're going to do something a little bit extra as well, because one of the great advantages of writing our own methods is that I get to decide what parameters they have, right? So when I, as the professor, give you a method and say, don't touch this, well, you can't touch it. But if you, as a student or a programmer, are writing your own method out of thin air, nobody can tell you what you can or cannot include in it. And so in this particular case, I'm thinking that it would be very helpful if I could include count and I as additional values down here that this method could also access. So I'm going to go ahead and stick those in my method call here as well. Oops, that's not how that's supposed to go. There we go, a little bit better. So this helper method, we can include additional parameters if we want to, if we need to help us solve this recursive problem. And so the base case in this situation is going to be based on the length of the array. If I is equal to values dot length, we know what our answer is. Our answer is going to be count. If I has gone off the edge of the array, if I had started at 0, we can see very clearly I has started at 0. Where does it go up? Well, I haven't done that part yet. We're getting there. If I starts at 0, it makes it all the way down to the end of the array. That means that I must have looked at every single value in that array. I must be done. So my answer is going to be here within count. Otherwise, we have more work to do. Let's look at the value in the array at position I. If it is odd, so I'm actually just ripping off this same exact if statement, as a matter of fact. Don't need to type it, I can copy it. Increment the count, but we're not done yet. We still have to do our recursive step. Now remember, we're keeping all of our recursion confined to our helper method. So I'm going to call my helper method again and think about how all of these values have to update. Our count we already took care of, right? I'm just passing this one along for the ride. But here is where we can take our I value and increase it by 1. So that the next time that we go through this, we're not going to look at I equals 0, we're going to look at I equals 1. And then the time after that, we'll look at I equals 2. And then the time after that, we'll look at I equals 3, so on and so forth. this is a complicated example, right? So I do want to step through this one in the debugger as well. Make sure you understand exactly what's going on here. You're going to be asked to write methods using helpers in Studio. So your TAs will be able to, review these concepts with you as well. But let's go ahead and walk through this. Ooh, I'm sorry, I'm really struggling here. Let's go ahead and walk through this example real quick in the debugger. I'm going to go ahead and set a breakpoint right here on line number 7, which is where the action begins. Okay, so here we are in our main method. I'm going to go ahead. Oops, I forgot to switch it out for the recursive one. Sorry about that. Let me switch it out for the recursive version and start it over. Okay, so here I am in the main method. I'm going to go ahead and step into so this is, again, my non-helper. Anything that only needs to happen one time. So variable initialization goes here, right? That's actually probably one of the main things that you're going to see is variable initialization happen in your non-helper functions, but there's other things that can happen too. Excuse me. And so I can step through here. I need to, step through here, set up those two variables, and then jump into my recursive call. We can see that I is set to 0. So we have not hit our base case yet, right? We've not hit the end of the array. So we're going to go down here and we're going to ask, is this an odd value? I don't actually care if it's odd or not. That's not really important to me. I'm more interested in the recursive substructure. It tells me that it is. Okay, I'll believe you. And then it says, all right, now I'm going to look at the next one. It's passing the count along, as well as incrementing I by 1. When we step in here, you can see that, okay, I now have 2 versions of this on my stack. Here we go. Still have not hit my base case. So I'm going to jump down here and say, all right, are you odd? No, you're not. So let's scooch over and check the next one. Here we go. This time it did find an odd value. Then we're going to go through one more time. This one is not odd. And then I believe, are we at our base? No, we're not at our base case yet. We have one final value to check. And now we should be at our base case. I is equal to 5, which is the length of our array. And we know what our answer is. Our answer is count. So there are 3 values. Think about, though, the fact that you can see that on this one over here, the stack is all filled up, right? It's got all of these still waiting, but there's no work to be done, right? There's no multiplication listed here. There's no addition listed here. Somebody in chat is asking, why, could I put count here and say 1 plus something? Maybe you could do that. I actually think that you could. I just didn't do it that way. I chose a slightly different way of doing it, but I think that you probably could come up with a solution that works that way. I think what's important to note, though, is that what's happening is that this value of 3 is basically just being passed the whole way up, right? So I'm taking the value of 3 and I'm passing that up to this one, who's going to pass it up to the one there, 3, 3, 3, 3, 3, 3, 3, 3, all the way back up, the line. That's how I'd expect it to work. Here you can see, all right, count odd helper returned 3. Sure it did. And then it's not going to even show me all of them, right? It won't even show them all. It's just like, yes, it's 3 all the way up. It's 3. And then finally I get to the very last one. Back in my non-helper method, right? And I finally get my official value of 3. get printed out here. Okay, so again, important to understand that regardless of what recursive operation you're performing, how that's actually happening, they all kind of execute basically the same. Create a whole bunch of recursive methods until I hit that base case, and then start resolving them all the way back up to the top. That's always going to happen, regardless of what recursive problem it is that you're trying to solve. Some other issues that trip people up, sometimes people will forget to put this return here. And then, yes, Eclipse will give you an error, right? So think about what it means if I forget to put return here. Think about what that means. First off, I'm breaking a rule. The rule says that no matter what path I take through this method, I have to give you an int. I have to tell you an int that is the answer. And if I take the return statement out, this else statement is not telling me what the answer is. It does not tell me what the answer is, right? Another way that you might want to, think about this, you can rewrite this a little bit differently to maybe help you understand what's actually happening when you do these recursive steps, or when you do those recursive calls over and over again, right? So here, right, I'm actually saying, all right, go figure out how much is left, tell me the answer, and then that just must be what the answer is. This is exactly the same as how I had it written before, but you do have to have an answer, whether you're at the base case or not. You do have to return something. You have to return something. It's absolutely 100% required. If we looked at the substitution method for this, though, it does kind of make things a little bit simple for the substitution method, because once you get down to the base case, you would you'd have your array, your count is 3, and I is equal to 5. Once you get down to the base case, you know what the answer is. And so then it's just going to be equals 3, equals 3, equals 3, right? The whole way back up. So it does kind of make the substitution method a little bit easier. Again, though, you have to look at the code. The code is what's telling me whether there's an actual operation to be performed here or not. The more important thing to understand is that this is just how methods work, right? The methods trace, the methods execution stack, all of those methods sitting there waiting until the base case gets hit. That's how methods work. That is the topic we talked about last week. If you understand how method execution works, then hopefully that is not too terrible of a concept for you to latch on to. I know I'm not doing the best job right now. My brain is like half here. I'm trying. I really am trying, y'all. I hope that I'm at least making some amount of sense today. I do have one more example that I'd like to talk about, and with this example, I would like to address the question that was asked earlier, which is why? Why would we use recursion instead of loops? And so for the examples that I have shown you so far, factorial and the array example, I can tell you with 100% certainty that if I was asked to do these, and I could choose whichever way I wanted, I would not use recursion for those. Never would I choose recursion for those. Maybe if I was bored or something. But if it is possible to do it with a loop, most people I think probably would prefer to do it with a loop. There are some people who really like recursion and will try and cram it in there every chance they can get. But most people I think agree that loops are a bit easier to understand in most situations. There are certain problems, however, that lend themselves very well to recursion. We are going to see some examples of these problems in this class. And if you go on and take some advanced computer science topics, specifically classes like 247, which is the class that a lot of students take right after this one, you'll see many different types of problems in which recursion is, the clear solution. It just is a good fit for the problem. And so one class of problems that works really well with recursion is called divide and conquer. And I'd like to show you an example of a divide and conquer problem now. It uses drawing. So we're going to be drawing some graph paper. Graph paper with, just grids. I'm going to be drawing grids on the screen, right? And so if I run this program right now, I believe it does a whole lot of nothing. Let's see. Let me just make sure. Yeah. So a whole lot of nothing right now. This is technically, a grid. It's just got one very big, very empty cell in it. But what I would like to do is, actually draw some lines on here and make a proper grid. And I'd like to use recursion to do it. So the instructions here tell us to draw one horizontal line and one vertical line to divide the square into 4 sections, where the square is given to us by these bounds. This is being the lower left x coordinate, the lower left y coordinate, and the size of the square. So I can do that. I can say standard draw dot line, and I have to specify where I want these to go from. So oh my gosh, this math might be, I drank some Dayquil before class, and this might be a little bit too much for me right now. Let's see. Excuse me. It's gonna go from the oh boy, size minus lower left. No, wait, it needs to go. All right. Do over. X, Y, X, Y. So I need the X coordinate for the first point, the X coordinate. Yeah, gotcha. So I'm going to draw the vertical line first, starting at the bottom. I know that the X position for the bottom should be the lower left X coordinate, which is the bottom left corner of the square, plus the size over 2. Yes, that's correct. And then the Y coordinate for the bottom of the square should just be the lower left Y, because that'll be the bottom. The X position for the top will be the same, right? Plus size over 2. And then it'll be lower left Y plus the size to get me to the top of the square. Let me go ahead and run this and make sure that this line is actually drawing properly before I try to draw the second one. Okay, good. Yes. I am still not too sick to compute the endpoints of a vertical line. Not yet anyway. Let's do the horizontal one. It's going to look very similar. So starting from the X coordinate, and now we're traveling horizontally. So it's going to be from size over 2 is going to be the Y factor now. Let's see, make sure this actually does it. Okay, good. I think you all would agree that I now have a little bit more graph paper looking like than I did before. But we haven't done any recursion yet. And what I would like for you to all notice now is that if I wanted to continue this, I could continue this in 4 different directions, right? I could take this big section, I could divide it into 4 different quadrants. I've already kind of done that, right? And then I could say, go draw graph paper on this top left quadrant. Go draw graph paper on this top right quadrant. Go draw graph paper on this bottom left quadrant. Go draw graph paper on this bottom right quadrant. And just repeat that for all 4. So let's go ahead and do that. I'm going to start with the lower left-hand corner. So what do we need in order to draw this, I need to know the lower left x coordinate, the lower left y coordinate, and the size. What information do I have? I have the lower left x coordinate and the lower left y coordinate of this entire very big square, which is 0, 0. And I have the size of this very big square. So I want to know what the lower left-hand coordinate of this square is in the bottom left. Well, that's actually very easy, right? That's actually probably the easiest one of the four for us to determine. So I can type in lower left x, lower left y. The size is just going to be divided in half, right? Because the width of the square, of this square, is half of the width of the big square from which we originated from. So let me go ahead. I've only done part of this, but let me go ahead and run this now and see if we can notice a difference as to what happens. Okay, great. So that time as I ran the program, you could actually see that it is traveling towards the bottom left-hand corner, drawing that cross in the middle of the square each time. So let's think about that. We can actually run this through the debugger. I think that would be a great thing to do, just to make sure we understand what's happening. Here I am on line 51. It's telling me to start in the lower left-hand corner, 0, 0, with a size of 1. That's the entire canvas, right? So if I step into this, this is my base case. I actually haven't spoken about the base case yet, but now is as good a time as any. When do we stop? Consider that as I keep drawing those crosses, eventually they'll get so tiny that I won't be able to see them anymore. So this is really telling me, how big do I want those little squares to be when I'm done? And you can tweak this number to kind of adjust the size of the squares to get what you would want accordingly. So, okay, we're going to keep going through. This should draw my vertical line. There it is. This should draw my horizontal line. There it is. There's my horizontal line. We're going to wait half a second. That actually doesn't help us right now. And then we're going to go to the lower left corner and start the process over again. So same coordinate, but now the size is divided in half. Okay, let's step into that. Have I hit my base case yet? No, I have not. So I'm going to go over and I'm going to draw a line. But notice my size is smaller now. So when I draw this line, it's going to draw it inside of this square here, like so. Same thing for the horizontal line, right? Like so. And there's my cross. Where do I go next? My lower left x, lower left y don't change, but my size is getting divided in half again. I'm trying to isolate this square now, right? This square. So I'll keep going. Oops, I hit the, shoot, I hit the wrong button. No, that's okay. Shoot, I hit the wrong button. But anyway, it did in fact proceed along through the lower left-hand corner again until it hit that base case. And then it said, okay, I don't have any more work to do. But what about the other corners? Well, we have to incorporate those as well. And since this is a divide and conquer problem, what that tells us is that I'm actually not going to see just one recursive call. I expect to see multiple recursive calls, one for each of the divisions that I'm expecting to conquer. So because I have 4 quadrants that I'm expecting to draw, I expect to see 4 recursive calls here. This one we just did is for the lower left. I'll label it as such. We can do the upper left next. So now I need to figure out, how do I get this coordinate here? If I start with this big square, how do I get this coordinate? My x coordinate isn't changing. My y coordinate is going up by size over 2. And then the square is still shrinking in half by size over 2. This should do my upper left quadrant. Let's try it though. Let's stop this. Run this program again. Okay. Yeah, there we go. Cool. So you'll notice that not only did it affect this upper left quadrant, but it also changed the lower right one as well. And you can see that some of the upper left quadrants in the lower one are starting to get filled in, right? Let's keep this going. We've got 2 more quadrants left in our example. We have to do the upper right quadrant next, which is actually the hardest. It's going to be lower left x plus size over 2, lower left y, plus size over 2, size over 2. Oops, forgot a division. We'll double check this one more time. So there it goes into the lower left. And you can see once it hits the corner, you can tell which ones it's going to do. It goes 1, 2, 3, 1, 2, 3. It's kind of mesmerizing, right? It's taking too long, in my opinion. Let me shrink this a little bit. I like watching it, but I don't want it to take that long. There we go. That's a little better. Yeah, this is a really fun one. For me, anyway. Cool. And there finally made it to the upper right quadrant. Starting to fill it in. Okay. Just this one quadrant left. You'll notice that none of the squares that have been identified have their lower right quadrants filled in because we have not yet written any recursive code to cover that. So let's go ahead and do that one more time. For the lower right quadrant, the x value changes, but the y value, excuse me, does not. So it'll look something like this. And yes, I believe that should do it. Nice little grid shape that's going to fill up the whole screen if I let it run. Now, a couple things to keep in mind with these divide and conquers. If you let these run, so consider that before we saw that execution stack was building, right? So building. That was filling up with method calls. Consider how many method calls are going to be happening now. I'm not doing just one method call per recursive call. I'm doing 4 of them. This is why it's called a divide and conquer. It's gonna expand out in 4 different directions at once. So if you actually take a look, at what the stack looks like once you hit the base case, you can see that it's going to have a fair number of recursive calls. I could shove a whole bunch more on there if I make this even smaller still and try to speed this up a little bit. See how much I can push my computer today. Look, you can see how tiny I've made that. See how tiny I made those grids. Still drawing them very faithfully. Let's see how much. Yeah, so you can see that, the number of method calls that can pile up on the stack here, it does get to be a lot. And the reason that I bring this up is because we do care about this. This is something that we care about as programmers. One common error that you might see if you do not write a recursive method properly is something called a stack overflow error. A very common error. And basically what that means, this stack it's not infinite in size, right? There's only so many methods that you can call before the execution stack is going to give up, be like, hey, I can't. You're calling too many methods, can't keep track of them anymore. It's too much. And when that happens, it's called a stack overflow. Now that number is very high. you are not going to hit that through normal usage. It is, again, typically an indication that something has gone wrong. But if you want to see, like we can force it with this factorial example, we can force a stack overflow. Consider this is going to count downwards from 5, right? So if I set my base case to stop when n is equal to 6, well, this is never going to hit the base case, right? This will never hit the base case of 6 and is starting at 5 and going down. I just broke this. I just broke this horribly. It's never going to hit the base case. This is a badly written recursive method. And if I try to run it, I would expect it to tell me that there's a stack overflow error. Here it is, right up here at the top. How many times did it call that method before it decided to give up? This many times. However many times you see listed here on the screen. I'm scrolling right now. I'm scrolling, bottom, right? So that many times. That's how many times it will try to call your method before it gives up and says, something's not right here. I think you made a mistake. I don't think this is going to work, right? So you can see that it's a lot. It is a non-trivial amount. This is not something you should hit on just through writing normal recursive methods. But if you do see this, it's an indication that you're not hitting your base case. That is the number one thing to check at. You're not hitting your base case. Make sure that if this is going down, that you'll eventually have a base case that you're gonna hit. Otherwise, you'll run into that stack overflow error. There was one other thing that I wanted to mention. It was right on the tip of my tongue, and I just lost it. Shoot. Oh well. Is one of these still running? Why could you not do this with a loop? You absolutely could do this with a loop. I never made the claim that you couldn't. I simply made the claim that some problems lend themselves much better to recursion. And I believe this to be one such problem. I do not think that it is the case that there is a problem that can only be solved with loops or only be solved with recursion. To my knowledge, that is not a statement that can be made. I think it is always going to be possible to try and force it to go the other way, but it doesn't necessarily mean it's going to be a good idea. Yeah, and as programmers, that's something we care about, especially as we get farther and farther along. Doing it this way can be faster because I'm literally doing more work at once than if I was using a loop to do things one step at a time. Hence, divide and conquer. It's a very, very powerful technique. And so speed also becomes a consideration, not just correctness. All fantastic questions, though. Absolutely fantastic questions. Okay. I think that is all that I had on my agenda for you for today, and I need to go lay down. So I think I'm probably gonna wrap it up here. Again, I would like to thank you all so very much for your patience. I know that doing class on Zoom today is not ideal. I'm trying. If you have any questions, please let me know. Please make an appointment, come in to see me. I'll go through this whole lecture for you again in my office, if that's what would help you. And yeah, take care, everyone. I hope to see you back in class next week. Thanks, everyone. Thanks for the well wishes.